boys and girls, dear viewers, my name is Binz, and this is a new episode in the Shapez BEASTMAM series. Last video, we started our new subchapter about the calculation of the remainder. I showed you how you can create a subtraction module, and today we're going to start having a look at how that principle has been implemented in the actual factory. Ironically, however, in order to do that, we must first look at something else, and that has to do with the specific nature of this machine and how signals come out of the decoder's clock. Whereas in the simple example module we set up last episode, I mindlessly provided a side input, or well, in this case, a bottom input, a filter input, by just running a constant shape signal into it. It turns out that in the actual machine, it's not quite as straightforward to actually provide that filter input. Because when the floating piece shapes are barfed out by the clock, actually quite a number of shape value manipulations and modifications are still needed before we can effectively forward that input to the subtraction module. And that's what I'd like to have a look at today. Now, if I might toot my own horn a little bit, toot toot, I think I am allowed to say that I've come up with something quite ingenious here. And that is that I have found a way to kill two birds with one stone. This conversion module, not only will it provide the side input for the subtraction thingy, but I've also managed to include all of the virtual combining that this decoder will require. I remember that in the first episode I presented you with, among others, the problem of where various modules would have to go. What, between painting and stacking and smelting and so on, what the order of operations would have to be. And one of those operations is combining, a concept that is unique to Shapez Industries and that you won't get confronted with if you're playing vanilla. And now, it turns out that if we build a combiner module here and now, then it will not only provide the side input for the subtraction module, this will also be all of the combining we will need to do. No other virtual combiners are needed elsewhere in the decoder if we play our cards right. And that's why, even though we're in the subchapter about the remainder, this episode is called Combining. Now, in order to get what's going on, once again, we need to return to considering the kind of floating shapes that may be coming from the clock. There are 6 types, we talked about them, we elaborated on the code symbol that each of them received, and we also talked about this conversion into a secondary set of codes that fused 2 different parameters to one code set. The colors in this set refer to the shape height. Red means the float piece has 2 layers, green means 3, and blue means 4. And we already went over how we stripped the color from that code and how and where we used that. So now it's only the shape forms that remain, and they symbolize not the height of the floating piece, but its vertical position within the target shape. More specifically, which base layer it has. A circle is used for floats that have their base layer on layer 1. The rectangle accompanies floats with their base on layer 2, and the star, finally, corresponds to those floats that have base layer 3. And here's the thing. This is not something I can explain, but rather something you have to realize that is actually always going to be true. 2 seemingly unrelated dots you've got to connect. All of these floating pieces, whatever they are, and whichever combination of float pieces comes out of the clock, you can always combine them with one another. Regardless of their height, you can always combine them with one another if they have the same base layer. Let that sink in. You can put any 2 floating pieces into a combining step if their base layer is the same. And with that realization, the entire combining thing actually becomes a lot easier than I had initially feared it would. Have a look at this. If the shape on the left is the one we need, for example, and the clock outputs the two float pieces on the right, then, because they both have the same base layer, in this case layer 2, which is symbolized by the green color, then we can combine those pieces without giving it any further thought. This is what comes out, and that is something that in this case we could simply put on top of the red layer. And there is an additional benefit to this as well. This combiner step also serves as a duplicate checker. I've got 5 clocks, and if they get loaded up, then in their initial state, they will all output the same floating piece. But what happens if you put identical shapes into a combiner? That's right, you just get the same shape again. And that means that while I have 5 clocks that may or may not be outputting the same value, even if I had 500 or 5,000, it wouldn't matter because all duplicates will always be reduced to just one output. And with those observations, even though elaborate, the approach becomes rather straightforward actually. We've got 10 input wires on the left right here. 5 of them contain the actual floating pieces from the clock, and each piece is accompanied by a code shape that's going to be either a circle or a square or a star, indicating what the base layer of that piece is. And so I run all of the code shapes into comparing units, see it right here, as to determine which pieces need to be combined with which ones. Again, this is a tick synchronized module that combines up to 5 shapes per layer because we have 5 clocks, and out the other end, right here, come up to 3 combined shapes. 1 for base layer 1, 1 for base layer 2, and 1 for base layer 3. And then there is this final step, which isn't necessarily complicated from a conceptual point of view, but rather confusing in terms of making sure you connect all lines and wires properly. So now, we might get up to 3 combined float piece chunks, right? Like for example, these 3. Within the main structure, these pieces are located on layers 1 and 2 for the leftmost shape, 2, 3, and 4 for this middle one, and 3 and 4 finally for the rightmost one. Now, pay attention. The subtraction module. As we discussed in the previous episode, it can only handle a flat input. So all in all, we will need 4 subtraction modules, 1 for each layer of the shape. And that means that from these 3 combined shapes, we will need to extract the layers one more time and then combine the matching layers with one another again. You can see that at this point, it becomes very useful to work with test shapes that are as consistent and transparent as possible, because that way I can now tell that green has to go with green and blue has to go with blue, white has to go with white. So let's do that. Right, so that's how that works. Now, on the wiring layer, it's now going to be a matter of keeping a very good overview over which wires you connect to which. And since you don't know in advance how high the combined pieces are going to be, it's easy to walk into the stacker versus unstacker trap we previously elaborated on. So in order to make sure we always get the outcome we want, no matter what the input, first of all, we will layer correct these pieces with a layer correction module. So let's build that in. And now that we've done that, we can again combine the layers that are the same across the three pieces. If there are any overlapping quadrants in those pieces, then again, it won't matter because the combiner will deal with any overlap. That's what it does. So now let's feed the layers into the correct combiner modules. Give me a sec. And we get 4 outcomes. These 4 outcomes together make up all of the quadrants that are contained within the currently selected set of floating pieces separated per layer. And those are the values we will need as the side input of our subtraction module later. Now, there are still some optimizations to be made here, like, for example, a combined piece that has a base layer 2, right? This middle module right here. It can never be 4 layers high. And a combined piece with base layer 3 is always going to be 2 layers high in practice. So it's not actually necessary to provide 4 output lanes to all of these layer correction modules, nor is it required to provide 4 input lanes for all of the combiner units. So these modules can be simplified a bit, which is what I have done in the actual machine, right? You can see that right here. Also, the modules in the example were not tick synchronized, which has also been done here. But other than that, that's the approach I took. So you can see with this algorithm, the entire concept of combining isn't a separate or independent step in the decoder's process. Instead, it's a method by which we can obtain a given set of values. It is a tool instead of a target. We don't need to take into account whether or not to use the combiner, and if so, when and where. We can just carelessly shoot all of our shapes through this combiner setup and let the machine figure out the rest, right? Isn't that nifty? And now that we've obtained the side input that we need for the subtraction module, next episode I will walk you through how that one works in practice. So be sure to subscribe to the channel to satisfy your FOMO, leave a like or a comment, all that good stuff, and then I would love to welcome you again next episode. Thank you very much for watching. Have a great day. Bye.